Good morning, this is your Stats Sensei, Mr. Spensei, and this is on the one sample proportion confidence intervals, and the scenario is this stuff is Primo. So a technology company manufactures lithium ion batteries for smartphones in three different qualities: premium, standard, and economy. So we're manufacturing batteries and we have three different levels. All right. The defect rates for each grade are well documented based on years of production. Premium grade batteries have a 2%. Sounds important. Standard grade batteries have a 5% defect rate. And economy grade batteries have a 10% defect rate. The company sells premium batteries at the highest price due to their low defect rate, while standard and economy batteries are sold at progressively lower prices. Recently, a warehouse manager discovered a large shipment of 25,000 batteries. Oh, so we have this sounds like to me, that sounds like a population. Sounds like we have a population of 5,000, 25,000. That's a big population without any labeling to indicate their grade. Okay, so we have 25,000 batteries and we don't know if they're premium, standard, or economy. The company needs to determine which grade these batteries belong to so they can be priced appropriately. To estimate the defect rate, the company randomly selected 300 batteries. All right, nice to hear the word random. That's going to be our first condition. And we know that our sample size in this case is 300. And found that 823 of them were defective. So this looks like this right here is 23. So it says create a 99%. So we know our confidence level, our CL, is going to be 0.99 for the proportion of defects in the shipment. So we're doing a confidence interval. So here's our basic confidence interval formula. Our sample proportion plus or minus Z star. And then we have the square root of P hat times 1 minus P hat. Please take note of this. Hypothesis test, this is going to be a P. For a confidence interval, this is always P hat. So please note it's P hat when we're working for a confidence interval. Please make sure of that you have that. All right, the next thing we need to do is we need to record what our important information is. Well, we see real quickly that we have 23 defects out of 300, confidence level of 99%. Now, they didn't give us P hat, but P hat is simply X divided by N. So this 23 divided by the 300, let's do that real quickly. 23 divided by 300, and we get 0.076, and it keeps going on. All right. So we now have P hat. We also have N. So we have everything we need to plug in but Z star. So to calculate Z star, we're going to have to go do an inverse norm. So if I go second vars, inverse norm, clear, parenthesis 1 minus 0.99, close parenthesis, divided by 2, 0.1 degrees of freedom is left, and I end up getting 2.5758. Please always make it positive. One thing to remember is when you're drawing, first off, we're going to be one thing to remember is when we're drawing it, we always, for a confidence intervals are always centered on P hat. So we are definitely centered on P hat with 0.0766. There's our interval space, and we'll have a lower bound and an upper bound. We also now have the information to plug into our formula. So plugging into our formula is P hat, our sample proportion goes right here. The 2.5758, the Z star, plugging that in. And then, of course, please remember, as I said before, when we're working with a confidence interval, we're plugging in P hat here, not P. Okay. And we have a sample size of 300. So that's us, all of us plugged in. And of course, we're going to be running a one proportion Z interval. So let's go ahead and run this test real quickly. I'm going to go stat, test, all the way down to letter, I believe it's letter A. Yes, it is 1 proportion Z interval. And we have 23, and our N value is 300. And we have a confidence level of 0.99. Do that again real quickly. And there we go. And we have our lower bound of 0.0371 and an upper bound of 0.116. And there's our p hat to confirm that we actually have the right value. And as we said earlier, we're going to be running a 1 proportion Z interval. And in the event there's some confusion on that, I'm going to go stat test and rerun that test, drop down to 1 proportion Z interval, which is letter A. And my X value is 23. My sample size is 300. I have a confidence level of 0.99. And we're going to calculate. And we end up getting 0.0371 with an upper bound of 0.162. All right. So that's our lower bound and that's our upper bound. And you can see that, hey, 766 is right in the middle of that. So what was our parameter? Well, let P equal the true population proportion of defective batteries. As I said in a previous video, please note we're working with proportions. We don't want to see the word mean there. So population proportion of defective batteries in the batch. The next thing we need to do is check our conditions. Well, they told us right at the very beginning, they said they took a random sample of 300 from a population of 25,000. So random a sample of 300, and that was given to us. So we're good there. The next thing, we need to make sure that our sample size wasn't too big. So we're going to take our sample size and multiply it by 10. When we do that, we get 3,000. That's less than our population because this is our population size. So N is less than 10% of the population. So we're good with that condition. The next one, we have to make sure that our sample is big enough. All right. And this is different when we're from our hypothesis test. When we're working with a hypothesis test, this was P, but for confidence intervals, this will always be P hat. So our sample size times P hat. So 300 times 0.0766. That's 2298. That's greater than 10. That's good. We're always comparing to 10 for this. And then 300 parenthesis 1 minus 0.0766. 277. That's also greater than 10. So our sample is large enough. So we met our conditions. By the way, I like to refer to these two as the Goldilocks. And here's why. Not too big, all right, or not too small, but big enough. So not too big, not too small, just right. So we have to make sure that we're greater than less than 10% of the population, and we have to be greater than 10 when we multiply things out. So all of that was done. We'd already calculated our intervals, so we need to write our first conclusion. Well, what are we? Well, we're 99% confident that the true population proportion of defective batteries, and I want to point this out to you, true population proportion of defective batteries in the batch. That's just a restatement of our parameter right there, lies within the interval, and this is the interval that we calculated. So this is the interval that we calculated previously above. And then finally, in repeated sampling, we expect this method to capture the true population proportion of defective batteries in the batch. How often? 99% of the time. All right? In repeated sampling, we expect this method to capture the true population proportion. And by the way, once again, I want to point this out to you. True population, that's a bad color to highlight with. I'll go back to this. The true population proportion of defective batteries in the batch. That right there, that part right there, once again, is a restatement of my parameter. So this is my parameter. Okay. All right. I hope that helped and look forward to seeing you on the next one. Thank you.